Okay, I think we can start. So, good afternoon, all of you. Thanks for being here. So, we're going to discuss continuations, the magic behind virtual threads. Virtual threads is actually part of Project Loom, and it is released as a final feature in Java 21. And it promises to bring high scalability to Java. But the real hero of the story is continuations. We will see that how continuations enable virtual threads to provide this high scalability in this talk. So that is going to be the theme of this talk. But before we start, I want to do a quick poll around in this room. So I assume that everyone here has heard about virtual threads. But is there anyone who has not heard, or this is the first time they are hearing about virtual threads? Please raise your hand. Oh, I see one hand there. Another hand. So especially for you guys, we have a very quick intro to virtual threads, so you will be along in the same way. And then, so for the rest of you, have you actually used virtual threads? Maybe not in production, but just in your dev environment to play around, create some virtual threads, see them running. Raise your hands if you have done that. Okay, quite some people, maybe 10-15% of this room. So that's really good. Thanks for raising your hand. Actually, this talk has 3 parts. In part 1, we'll do a very quick intro to virtual threads. In part 2, we'll look at continuations, and then continuations in Java. And in part 3, we will actually use that understanding of continuations to create our own version of virtual thread. Okay, so let's get started. Very quick intro about me. My name is Balkrishna Rawool. I work for ING Bank. Okay, let's start with part 1. Introduction to virtual threads. Now, what we see here in this picture is that we have a JVM instance, and it is running on some operating system. Also, it has a large number of virtual threads, some platform threads, and OS also has some OS threads. Now, let's start with platform threads. So, platform threads are the threads. They're also known as threads. They are present in Java for a really long time. They are the so-called OG threads. And they are actually a thin wrapper over operating system threads. What that means is when JVM wants to create a new platform thread, it requests operating system to create a new OS thread. And only when that thread can be created, it creates a platform thread. That means then these threads map to OS threads with a one-to-one mapping. So a platform thread instance has exactly one operating system thread connected to it. And because platform threads, creating a platform thread is a resource-intensive task, you put them in thread pools. So when you're done with the platform thread, you don't throw it away, you put it in a pool so that next time when you need it, you can use it from that pool. Now, virtual threads, on the other hand, are lightweight user threads. Lightweight meaning they require significantly less memory. And that means you can create them in abundance, you can create them in huge numbers, like millions, and that makes them highly scalable. There's actually one more thing that makes them highly scalable, and we'll see that in a few minutes. With virtual threads, you don't pool them. There is no need for pooling because creating a virtual thread is a very cheap operation. You create one when you need one. When you're done with it, you just throw it away. And next time if you need it, you create another one. In fact, pooling virtual threads is an anti-pattern, so don't do that. Now, if you look at this picture, we see a large number of virtual threads. We see some platform threads, but some of these virtual threads are connected to the platform threads. Why is that? That is because a virtual thread on its own cannot execute anything. So it requires a platform thread to execute something. But then there are still virtual threads which are not connected. What about those? For those, we have virtual thread scheduler. So this is a new scheduler introduced along with virtual threads. And what it does is it actually mounts a virtual thread onto a platform thread when a virtual thread requires platform thread, and it unmounts the virtual thread when the virtual thread does not require platform thread. Now, what would be the scenarios where a virtual thread would not require platform thread? This is when a virtual thread is waiting for something. For example, it is waiting for a network resource to be available or a database to return something. In those cases, a virtual thread is not processing anything. It is just waiting. So it does not require platform thread. It does not require CPU. So it gets unmounted from the platform thread. And in a typical IO-bound application, threads spend a lot of time waiting. And if we use virtual threads, we will avoid that waiting. Meaning only virtual threads would be waiting, and the platform thread would not be waiting, and that way CPU is not blocked. So when you use virtual threads, your CPUs are very highly efficiently utilized, and that makes virtual threads highly scalable. And also in this entire endeavor of mounting and unmounting, the platform threads are carrying virtual threads, so they are also known as carrier threads. Okay, that's a lot of theory about virtual threads, but now let's see them in action. Let's create some virtual threads. I hope the font is big enough. In the back, can you read it? No, you need even bigger? Okay. How about now? Yeah? Oh, I still hear no, so let me just make it even bigger. Should be okay. Yeah? Okay, I'm not sure if I get a yes, so let me make it even bigger. This should be okay. Okay. I didn't really practice with this big font, but we'll see. There might be too much text on the screen, but for now I think we are okay. And while we are at it, let's also increase the console font because we will still see some stuff on the console. 30 it is. Okay, so before we create a virtual thread, let's create a platform thread. And with Project Loom, we have a new API to create a platform thread, and you do thread.offPlatform. This gives you a platform thread builder, and onto that you can call start, which would start a platform thread. And we can pass runnable. Here we just want to print the current thread. So if I do this, and if I run this, I should see a platform thread, and that's what I see here. Now you can imagine a similar API called offVirtual. If I run this, because this gives me a virtual thread builder, and again I can start a virtual thread from here. So if I run this, I get a virtual thread instance. Now if you notice the two-string implementation of two-string representation of virtual thread, you see a couple of things. One is this. So this is actually an ID of the virtual thread, and it is unique for each virtual thread. Also this part, this is a platform thread. In fact, this is the carrier thread of this virtual thread. And so this thread was carrying this virtual thread when it executed this statement. So we get some information about the carrier thread of the virtual thread as well. There's also a shorthand method, so I could simply do start virtual thread, starts virtual thread. We'll see it here. And there is another way to create a virtual thread, that is to use executed service. So I'm going to do that. Our executor, this will be executors dot new virtual thread for task executor. So this actually gives me an executor service, which is not really backed by a thread pool. So it gives me a new instance of virtual thread every time I request it. And the way to do that is basically executor.submit and submit a task. In this case, I again just want to print the current thread. And if I run this, I will see that it is actually a virtual thread. There it is. So using this, I can create a bunch of virtual threads. So let me do that. Okay, and now it gets a little tricky on the screen. But now I'm creating, I don't know, about like 9 virtual threads. And I use this try with resources. So this ensures that all these virtual threads are finished before I exit this try block. So let me run this. And I see all these virtual threads running. And if you notice this part, they are all unique IDs. That means these are all different virtual threads. But if you see here, for example, like these 2 virtual threads, their carrier thread is the same. So what that means is this virtual thread was mounted onto this platform thread. And when it was finished, it was unmounted, and a new virtual thread got mounted on the same platform thread. So basically, you see that mounting and unmounting in action. But how does this work? How are virtual threads mounted onto this platform thread? How are they unmounted? And in fact, the unmounting is the part that is driving the scalability. So what enables these virtual threads to get this scalability? And the answer to that question is, I need some drum rolls. The answer to these questions is continuations. So basically, now the part 1 is ended. So we are now going to start with part 2, where we will discuss continuations and continuations in Java. Let's start with what is a continuation. So a continuation can be viewed as a representation of the current state of program. So your program could be as simple as sequence of instructions, or it could be a bit more complicated with nested method calls or nested loops. And you can take a continuation of this program at any point in time. And when you take a continuation of this program, that continuation object would represent the current state of the program, including these nested method calls and the iteration of a particular loop that you are executing while you took this continuation. So basically, when you take the continuation, you get an object that represents the current state of the program. It actually pauses the program there, and you get a handle to the state of the program. Also, then you can pass this object anywhere in your program, and then you can decide to resume that program. So you can continue that program, and then it will run to its completion. So you can also view that that continuation as sort of the rest of the program, because it represents something that you can continue and then complete the program. So in a way, a continuation can be viewed as a representation of the current state of the program, and it can also be a representation of the rest of the program, the rest of the computation, right? What is the use of such an object? Well, using that, we can pause the execution of the program, and also we can resume it later, right? So this gives a power to pause a program and resume it later. Now we'll see that in action when we talk about continuations in Java, which we'll do it now. So how are continuations done in Java? We'll see that with some examples. But before we do that, it is important to note that the continuation API in Java is not supposed to be used directly by application developers. So our application should not directly deal with continuation API. For now, it is only used internally and only used to create virtual threads. Okay, then why are we discussing continuations API? What's the point in doing that? Well, 3 reasons. One is that it allows us to get good understanding of the behavior of virtual threads. Secondly, it tells us how are these virtual threads getting mounted and unmounted. Basically, how are these virtual threads getting this high scalability characteristic? And thirdly, because it is fun. So we'll find that out. Okay, so let's see continuations in Java in action. And let me open another file. So here I'm going to create a continuation object. In fact, I'm going to get it as a return type from a method called getContinuation. Let me create that method, and this would return a continuation. Okay, I just said that we are not supposed to use the API directly, but how am I able to do this? Because I have actually asked the compiler I basically set this argument in the compiler, which exposes everything in java.base. But a quick note, if you see this setting, it's an indication that your code is not supposed to reach production. So don't do this for your production code. We are just doing this because we want to get the understanding of continuation API. So it's okay for this demo. Okay, so this method will give us a continuation, and the way to do that is create a new continuation object. And when you create continuation object, it requires continuation scope. I'm not sure if you can read it in the back, but I can read it for you. So it requires a continuation scope and a runnable. So let's first create a continuation scope. So you can see continuation scope, for the sake of this talk, adds a namespace for your continuation. So we can pass a string here. It could be empty, but in this case, let's just pass demo here. And then we can use this scope. And the continuation also requires runnable. So let's do that. Let's pass a runnable. And this runnable, let's say, prints few things. So it prints A, then it prints B, and it prints C. And then we return the continuation. Okay, so now we have handle to the continuation. What can we do with it? We can run the continuation. And let's see what happens if we run the continuation. So it's basically prints ABC, which means it is running this runnable. So nothing fancy going on here. But because this runnable is wrapped in a continuation object, it gives us certain power, and that is to pause the execution of the runnable. So I could do continuation.yield, and then pass the code. So this will basically pause the execution of runnable, and I want to do it at 2 places. So with this, if I now run this program, I see that it only prints A. That is because it executed the runnable, it started with this line, and then it encounters this continuation.yield. So that pauses the execution of runnable. And it not only pauses the execution of the runnable, but also transfers the control here immediately after the continuation.run. So basically, you call a runnable, you pause it, and then you get control back. And you can do something else here. So I could actually say do something, and it will do that. So basically, it will run the runnable, pause it, and the control comes back to you, although the runnable is not completely finished. And how do you finish that? How do you continue the continuation? You just run it once again. So if I do run now, it will run the continuation, pause it, allow me to do something, then if I do run again, it will continue from the last yield point. So basically, the control came back here, and it executed this statement and encounters another yield thing. So it goes from the last yield point to the next yield point, and then it pauses there. How do you continue from there? Well, you run it once again. So then I see the continuation has basically run, paused, allowed me to do something, then run, paused, allowed me to do something, but I didn't do anything. I run it once again. What if I do it once again? Because now basically it has finished, the whole runnable has executed, it is finished. What if I do run once again? I get an exception saying that the continuation is already terminated. So, well, let's not do that. So if I do this, again, I see that this is the way you can have a runnable, run it, pause it, and resume it. There are a couple more things to notice about this call, and that is this continuation.yield call does not have to happen from the body of this runnable. So you could call a method and another method. So basically, this continuation.yield call could be nested in method calls. And if you have that, then your execution would pause at that point. So let's say you call a method from here, and then you call another method from there, another method from there, and then you have continuation.yield there. The execution would pause at that point. And then it would basically transfer the control all the way back to the point where you started or run the continuation, and then it'll allow you to do something. Also, second thing to notice is that this continuation.run also does not have to happen from this method. You get a handle onto the continuation, and then you can pass it around in the program. And then at anywhere in the program, you can decide to continue the continuation. Okay, so this control transfer, now it looks pretty abrupt, but how is this achieved? How does this happen? It is mainly happening with the manipulation of call stack. And we'll see that in a minute. So this is a totally different example than we just saw, which will explain the behavior of continuation.yield. So what is happening when we call yield? We have our stack and heap memory. So in this case, we start with the main method, and it calls a method A, a name which is very carefully chosen to be self-descriptive. And this method has access to a continuation object. And what it does is it calls continuation.run. Now, you can imagine you have a continuation when you call run on it the first time, it will start executing the runnable, right? So whatever happens now is happening inside that runnable. So the runnable first calls a method B. Now this method B calls another method C, and this calls another method D, very useful method names. But something interesting happens in this method D, and it calls continuation.yield. So now in your runnable, you have continuation.yield call. What should happen? The continuation should pause there, and it should also return the control back to the point which called the continuation, which run the continuation. So how does that happen? Well, the stack frames from continuation.yield until B, they are copied to heap, the heap memory. And in fact, they are copied inside the continuation object. So they are stored there. And your continuation.run method, that returns to method A. That's why we see that the runnable was getting paused, and we see that the caller is now resuming from the last continuation.run point. Okay, so this explains how the runnable is getting paused and how the control is getting transferred to the caller. But what about the resume part? Okay, let's take a look at now continuation.run. So you have a continuation, you already run it, you have paused it, and now you wanna continue, you wanna run it once again. What happens then? Again, you have your stack and heap memory. In this case, you have continuation object, which has these stack frames saved in it, right? Because it has partially run. And we have again our main method. In this case, it calls a arbitrarily different method called E. And this method still has access to continuation object. So this has access to the continuation object, and it decides to resume the continuation. It decides to basically continue the continuation. So what should happen here? Control should go right into the method which called the continuation.yield, and it should resume from there. Right? How is that achieved? Well, all the stack frames from the continuation object are now moved to the call stack. And then the continuation.yield method, it returns to method D. So this way, you basically get into the runnable, into the point where continuation.yield happened, and then continue from the next statement. So this explains that abrupt control transfer. Okay, so this wacky control transfer, what is it good for? Obviously for virtual threads and green threads. So if you want to implement virtual threads or green threads, you would use continuations. But also, if you want your own version of coroutines or exception handling, you can use continuations. Also, you can use them to write generators. Now, in this talk, we are actually going to explore two of these uses. First one is the generators, so we'll see that. And we'll also explore the virtual thread implementation in the third part of this talk. So let's start with generators. What is a generator? So a generator is actually a data structure that allows us to write a function that yields values. Normally, when you have a function, it gives you one value. But with generator, you have a function which gives multiple values, and not all of them at the same time. So these values are lazily retrieved. So this function gives you one value, you can use it, and then you can also ask to give more values. So that's what generator does. And you can then iterate over these values, iterate over the generator by using a loop. An example is here. So you have a generator written here, which is yielding A, B, C, and then you have a consumer, which is basically iterating over these values in a loop. What could be the use of a generator like this? Imagine you have multiple values, and these values are generated or created after a very heavy processing or resource-intensive calculations, something that requires a lot of resources. You don't want to do that up front, right? You want to do it only when it is necessary. So that's when you would use generator. And how do you implement this in Java? Well, writing a generator in Java is not that difficult. You can have streams. So streams also give you multiple values. They are lazily retrieved. So they are easily evaluated. So that's, if you have a stream, you already have a generator. Or you can also create a generator by using iterator or a collection of suppliers. So it's not that difficult to implement generator in Java. But what we are going to do now is we are going to implement a generator only using continuation. And we're not going to use streams or iterators or anything. So let's see how that could be done. Let me open a new file. So what we actually want to do is we want to create an object called as generator. And we want to be able to do something like this. So create new generator. So let's create this class generator. And generator returns multiple values. So let's pass a type argument so that we can get values of this type. And in our case, we want strings to be returned. So if you see here, we want A, B, C. So our generator, we want strings to be returned. And we want to implement generator using continuation. So let's define a continuation object here. And continuation requires continuation scope. So let's put a continuation scope in here. And let's write a constructor. So public generator. So this would basically initialize the scope, new continuation scope, and it could be anything. Let's call it generator. And then we need to initialize the continuation, which is basically using the scope and a runnable. So for now, let's imagine that it doesn't do anything. And now let's run the continuation here. Okay, so what do we want the generator to do? We want it to yield these values, right? We want it to yield A, B, C. So how can we do that? Let's say we have a lambda, which allows us to write some logic, and we can yield A, B, and C from here. But that's not how the yield keyword in Java works, right? So let's try to then make it as close to this implementation as possible. Let's say there is a method called yield where we can pass these values and it would yield these values. And that this method is defined, or this method is accessible on an object called source. Hang on a minute and this will make some sense. So we have this source object onto which we can call this yield method, and we get that source object as an input to our lambda. Now let's define a source type here. So we have a public class source, and then define a member variable of type source here, and then create the source instance here. Oops. And now this input to the generator becomes a consumer of source, right? So let's make this a consumer of source. Let's call it consumer. And the only thing that we do in the runnable is basically consumer.accept, and then we pass the source object. So that way, in the lambda, while we define the generator, we have access to source and we can call yield on it. So now the only thing that is left to implement is the yield method, and now our generator definition looks quite similar to the example that we want. So yield method, well, what we actually want is the generator to lazily retrieve these values, right? So basically we want it to pause the execution whenever it is retrieving one value. So the way to pause an execution is yield continuation.yield, right? And then we pass scope here. Also, we don't want to lose this value, so let's put it in a variable called value. And so this value is t. So we basically store the variable somewhere, and then we pause the execution. So this allows us to define a generator. Now, how do you use a generator? We want to be able to use generator in a loop. So how can we do that? Let's say we have a couple of methods in the generator, like this. So you have a hasNext method, which tells you if the generator has next values, and it has a next method, which gives you the next value in the generator. Now let's define these methods, and that way we have a complete generator example. So hasNext method is not that difficult, because generator has next values as long as you can continue the continuation. So this would simply return continuation.isDone, and actually negation of it, because generator has values as long as continuation is not done. And then what is remaining is to implement this next method. This should return object of type t, and basically it is something which is stored in source. So we could simply return source.getValue. Now let's define this getValue method in the source. Let's make this private. And basically we can return this value, and we actually want to continue the continuation. So we can do continuation.run here, but we can't do something after return. So let's put this in a temporary variable, and then return it after the continuation has run. Okay, so that way we have our generator implementation. And with this, we are able to define a generator, yield some values, in fact, yield multiple values, and use it in a loop. And we also expect that it actually pauses the execution after yielding a value. Now let's run this and see what happens. If I run this, yeah, I see ABC because it has iterated over all these values, and it has generated these values, and we can see them. Also, it pauses execution after each generation and passes the control here. So we could do anything here. We could actually, I don't know, do something, and it would basically do this part every time it retrieves a value. We can also decide to terminate the loop in between, and that way the generator does not execute the rest of these things. So this way we can write a generator using continuations. Again, I'll share the link to the source code so you can take a look back later. Because of this big font, I don't think like much part is visible here, but I'll share the link. Okay, so this is how you can write generator, and I wanted to show this example because I wanted to also highlight the fact that continuations are a general purpose It's a utility that you can use for many different purposes along with virtual threads. But generator is not what we are here for, right? We are here for virtual threads. So that's part 3. So now we are going to implement a virtual thread using continuations. A simple version of virtual thread, and it should have certain characteristics. So those are our goals for the virtual thread. What we want our virtual thread to do is a virtual thread instance should not use CPU or should not use platform thread when it is waiting or when it is blocking or when it is blocked. Now this sounds like a pretty logical expectation from a virtual thread. Also, a virtual thread can get mounted on several platform threads during its lifetime, and a platform thread can support several virtual threads during its lifetime. So basically that many-to-many relationship between virtual threads and platform threads should be there. Again, these are pretty reasonable expectations from a simple virtual thread. How would we go about implementing this? We'll start with a virtual thread class, so we'll write that. Then we will write a consumer, something which uses virtual thread, and it also makes some blocking calls. And then we will write a virtual thread scheduler, which will have a bunch of virtual threads and a bunch of platform threads, and it will basically schedule these virtual threads onto these platform threads. Again, this sounds like a pretty logical design. So let's go ahead and implement this. Starting with virtual thread. Let me create a new class called virtual thread. Oh, sorry. I had to stop the presentation and then switch here. Yeah, so now basically we have created this new class called virtual thread. And a virtual thread in the most simple form is nothing but a continuation, right? It is only a continuation. Of course, it needs scheduler to run or execute it, but a virtual thread class will only have continuation or only need continuation. So let's do that. Let's put a continuation inside it called continuation, and continuation requires scope. We know the drill, so let's create a scope here. In this case, we want to make it public static final continuation scope. Let's call it scope, and then we can initialize it. Let's call it virtual thread. Okay, so we have our scope, we have our continuation. Let's create a constructor for our virtual thread. And this constructor only has to initialize the continuation. So it does that. We can use the scope, and it requires a runnable, right? Something that it can run. Let's say we get that as an input to the constructor. Then we can pass it here. And then we need something to run our virtual thread. So let's create a run method. This will basically just run the continuation. And before that, it just prints something saying that virtual thread is running on thread.current thread. So it basically says which platform thread this virtual thread is running on. And IntelliJ asked me to use string template, so why not? Okay, so actually we have our virtual thread implemented. So this is all it needs. But in order to make it more useful, more usable, I want to add one feature, which is ID, identification of the virtual thread. So let me do that. For that, we create a private integer ID. And to set these IDs, I want to use a constructor. I want to use a counter, and it would be an atomic integer. So let's create a private static final atomic integer called counter, and starting with value 1. So all these IDs will start from 1. So this will be counter.get and increment. So now we have ID of the virtual thread as well, and we can actually print the ID here while it is running, or while it is about to start running. Okay, so virtual thread implementation is done. Now let's create some virtual threads. So let's create a new class called as demo, which will have a main method, and here we will create a bunch of virtual threads. So let's say vt1, which is a new virtual thread with some runnable, and let's say this virtual thread has few printlns. Basically, it says that I have 4 instructions, and those are 1.1, 1.2, 1.3, and 1.4. And then we create one more virtual thread, which actually has pretty similar implementation. The only thing is that it has these two instructions, which are 2.1, 2.2, 2.3, and 2.4. So this way we are able to create our virtual threads. But how do we run them? In order to run them, we need a scheduler. So let's create a virtual thread scheduler. Virtual thread scheduler. Yeah, and if we look at this picture here, we see that the scheduler has a bunch of virtual threads and a bunch of platform threads, and it schedules these virtual threads onto these platform threads. And what we want to use is we want these virtual threads to be scheduled in first in, first out manner. And it would be then handy to use a queue of virtual threads. So let's do that. We have a private queue of virtual threads called queue, and it is a concurrent linked queue. And for platform threads, again, bunch of platform threads will use an executor service. So private executor service called executor, and this will be executors dot fixed thread pool of, let's say, 3. So we have, let's say, 3 platform threads that we want to use. Yeah, so we have a bunch of virtual threads and a few platform threads. Now let's write a start method so that we can start the scheduler. We have a public void start. And what the start method does, it actually runs forever. And while it is running, it checks if there is something in the queue. And if there is something, it picks that thing up and then schedules that thing onto the platform thread by doing executor.submit. So basically now we have a simple implementation of scheduler with a start method, and then this will run forever, pick things from the queue, and schedule them onto the platform threads. And also we need something to submit some more virtual threads to it. So let's create a public void schedule method, which gets a virtual thread, and it simply adds it to the queue. So this way we are able to add more virtual threads, and then the scheduler will schedule them onto the thread pool of platform threads. Okay, now let's use the scheduler in our demo so that we can run these virtual threads. For that, I'm going to create a public static final virtual thread scheduler. Let's call it scheduler, and this will be a new virtual thread scheduler. And now let's run it on a platform thread. So new thread, scheduler start, and then start the thread. So this way it runs on a separate platform thread of its own. And now we are able to basically schedule these virtual threads onto this platform, onto these platform threads. So this way we have a scheduler which starts, we have a bunch of virtual threads that we are adding to the scheduler, and we are scheduling them. So now if I run this, what will happen? Well, these 2 virtual threads would be added to the scheduler, and they would start running one after the other, but it will happen so fast that they will run, they will feel like they're running at the same time. And then they will run parallel because we have 2 virtual threads and we have 3 platform threads, right? So each one gets a platform thread to run. Okay, let's actually see this in action. Let's run this. So if I run this, what I see is that virtual thread 1 is running on platform thread 1. Virtual thread 2 is running on platform thread 2, and they both basically print all these instructions, so they both are running at the same time. Now, what if I want to run them sequentially? Well, I could simply change the number of platform threads to 1. And now if I rerun this, I will see that virtual thread 1 is running on platform thread 1. It runs to its completion, and then I have virtual thread 2, which is running on the same platform thread because we have only one platform thread, and then it runs to its completion. So that way, we basically see them running one after the other. But I want to change this to 3 threads again. And now I want to add the blocking call in these virtual threads. So with the OpenJDK team, when they worked on virtual threads, and they created the virtual thread implementation, but then they also changed the entire JDK. In fact, all the places where there were blocking calls happening, they made those places aware of virtual threads so that they don't block the virtual thread. Now we don't have enough time to basically change the entire JDK, so we are only going to create something which will simulate the blocking call. But before we do that, I want to add one more feature here, and that is thread.currentThread. So now, if you see here, when I do thread.currentThread, I get current platform thread. It is not aware of our virtual thread, so we need some mechanism of getting our own virtual thread. And for that, I'm going to actually add a static member here, public static. This may not be the best way to get the current virtual thread, but this is good enough for our demo. Virtual thread, which will be current virtual thread. But now I have a question, because we want this variable to have different values for different platform threads, right? Because each platform thread would be executing its own virtual thread, and this will be different for each of those platform threads. So what do you use when you want a variable to have different values for different threads, different platform threads? Thread local, exactly. So we can use thread local here. So this would be a thread local of virtual thread, and this would be fine. But hang on, in Project Loom we have a better API, which basically is an equivalent of thread local. So we have a better API for doing something like this, and that is scoped values. So we'll use scoped value here, and we can also make this final, and this would be a scoped value dot new instance. And now we want to make sure that we have the right virtual thread. This scope value is set with the right virtual thread when we are running that virtual thread. And the way to do that is basically change this part to use the scoped value. So basically set the scoped value, set the scoped value to the virtual thread that we are executing, and then run the virtual thread. So this way, when this virtual thread is running, this value is set to the right virtual thread, and then we have access to the currently executing virtual thread. Okay, now with this feature, we want to create the simulation of our blocking call, and we're going to call that waiting operation, because it is a waiting operation when a virtual thread is blocked. And this waiting operation class will have only one method, which is public static void perform, because it performs the waiting operation, and it will take two arguments: name of the operation and duration, so that time it waits. And the first thing it does is basically it says I'm waiting for this thing for this much or this many seconds. And again, IntelliJ wants me to use string template, so let's do that. And now when a virtual thread is waiting, we actually want to pause that continuation, right? We don't want to execute anything. And the way to do that is obviously use continuation dot yield. And we also need to pass the scope, and this would be virtual thread dot scope. So this will ensure that our virtual thread basically does not use the platform thread. It gets unmounted because it will stop the execution. But our waiting operation should not only stop the execution, but it should also make sure that it resumes the virtual thread after the duration amount of times. So how does that happen? Well, for that I'm going to use a timer. Again, there could be a better way to do this. There definitely is a better way to do this, but timer is good enough for our use case, so I decided to use that. This will be create a new timer task, and we want it to resume after duration amount of seconds. So we said that, and we want to make sure that we cancel the timer. Also, we want to resume the virtual thread. But which virtual thread, you ask? We don't know which virtual thread it is, right? So let's get the virtual thread here, because that would be the current virtual thread when it was executing this, and we have it in here. So we have it in the scheduler dot current virtual thread dot get. That gives us the current virtual thread at this point, and let me use static import, and then we can basically resume it here. So we use demo.scheduler.schedule the virtual thread. So this ensures that we have the virtual thread resuming after the waiting is over. Okay, so our waiting operation is implemented. Now let's use that in our demo. So here I want to basically wait for something, wait for say network for 2 seconds. So virtual thread 1 waits for 2 seconds for network, and virtual thread 2 waits for database for 5 seconds. Okay, now let's say what happens. When we start the scheduler, again, let's see how many platform threads we have. We have 3, and we have 2 virtual threads. So when we start this, each of these virtual threads will get 1 platform thread. They will start running, and at this point, they will basically pause the execution. And at that point, no platform thread would be busy. And then after 2 seconds, virtual thread 1 will basically resume its execution, will get one of the platform threads, start executing, run to its completion, and then again, all the 3 platform threads are free. So then when virtual thread 2 starts its execution, it can use any one of these platform threads. So now if I run this, let's see if that is exactly how this works. So we have both these threads running at the same time with thread 1 and 2. They execute these 2 instructions, and then they start waiting. And I have virtual thread 1, which is running on platform thread 3 after it comes back. And then when virtual thread 2 comes back after 5 seconds, it starts running on platform thread 2. So here we see that this virtual thread, or this virtual thread 1, which is running on platform thread 1, after the waiting is over, it is now running on platform thread 3. So basically it moved from one platform thread to the other, so that mounting and unmounting, we see it here. And I also want to run it once again, because I want to also show that that we can have 2 different platform threads, or one platform thread which is basically executing 2 different virtual threads. So we see that now, because we now have this platform thread which was executing this virtual thread 1, and after the wait is over, it is executing virtual thread 2. So we see that many-to-many relationship also here. Okay, so I think all of these criteria that we set for our virtual thread is satisfied here. But hang on, these are virtual threads, right? So we can create them in abundance. We can create them in large quantities. So let's do that. Let's turn the heat up, and let's create, I don't know, maybe 1,000 of these, if not millions. So what we'll do is we will now have 1,000 of these virtual threads and 1,000 of these virtual threads. So we have 2,000 virtual threads waiting for some time, and they are running on platform threads, let's say 10 platform threads. And the only problem I see is the timer task, because this uses platform thread, but these are a few thousand, so it should not be a problem. So let's go ahead and run this. But before I run this, I want to show you something else. I want to show you another demo class, which I wanted to compare, but now it's like too big font, so not really able to see everything together. But if you see this demo class, the new one, it also has 1,000 of these things, but instead of virtual threads, it uses runnables. So it has 1,000 runnables, which are now waiting for 2 seconds, and 1,000 runnables which are waiting for 5 seconds. So exactly the same thing, but instead of virtual threads here, we have runnables here. And it also has a scheduler, but it only has platform threads, and there are no virtual threads. So basically, this is an equivalent implementation, but without virtual threads. Now let's see what happens if I run this. If I run this, it runs and runs and runs. So it'll just go on running. Let me put this onto right-hand side, and let it run. And while the implementation with only platform threads is running, let me go here and run the the virtual thread implementation. So implementation that uses virtual thread. So it also started running, and it is running. And well, something has happened. Let's see. Well, I see this virtual thread with ID 2000. So basically, the last virtual thread has finished all of its instructions. So basically, all the virtual threads have actually finished execution, while the platform thread equivalent is still going on. So what we see here is that with the same amount of resources, with the same amount of CPU, we can actually get more done if we use virtual threads. And that is the high scalability characteristics of virtual threads, provided you have a lot of waiting. So that's basically the final demo I had to show. And if you come back, yeah. So if you're, so this is the implementation. So if you are interested in the source code, it is present here, and you can also connect with me on Twitter with that handle. But just to summarize what we saw today, we looked at what virtual threads are. We looked at what continuations are, and we also used that understanding continuation to create our own version of virtual threads. And in that process, we learned something about the behavior of virtual threads. We learned about how mounting and unmounting happens with virtual threads. Basically, we learned what gives that high scalability power to these virtual threads. And I hope it was fun. Thank you.